I recorded it 2 or 3 months ago. So I'd say raise your brightness levels if you can. Let me see, how do I make this full screen? Here we go. Before I talk about the actual talk, my plan is to speak for about 40 minutes or so of prepared material, and I might pause from time to time when there are questions. I'll look for the hands and look for Shanta kind of yelling at me saying, Tim, you're doing the wrong thing, and I'll try to watch what I'm doing. But I have about 35 to 40 minutes worth of material, and I've sort of put in a few places where we might come back to it if we have more time for questions.
Yeah, so Tim, so I'll collect the questions, so then I'll tell, interrupt sometime if there's some pressing question. So at the end, we'll take more questions.
Oh, okay, great. Thanks very much, Shanta. I really appreciate that. So if I hit start here. Right, so I'm a very sort of old-fashioned number theorist, and what I try to do when I give a talk is to try to convince people why I'm interested in a topic. They might be interested, they might not be interested in it, but they might then see why I'm interested in it, why people might be bothered to investigate such a topic. So as I've written up there, the title of what I wish to discuss today is about the Riemann hypothesis, which I'll abbreviate throughout the rest of the talk as RH. So the title of the talk is that the Riemann hypothesis is true up to 3 times 10 to the 12. Now, what does that even mean? We'll get to that later. And as Tanvi said in her introduction, I'm at the University of New South Wales, which has a campus here in Canberra. And just to make the title even longer, it's at the Australian Defence Force Academy. That's what ADFA stands for. Everything I say in this talk is joint work with my longtime collaborator and dear personal friend, Dave Platt, who's in Bristol in the UK. Roughly speaking, I sort of handle the theoretical aspect, Dave handles the computational aspect, so if you have any technical questions, then absolutely he's your man to ask. So, the goal of this talk is to give a bit of a background as to what the Riemann hypothesis is, why people might be interested in it, and why I think it's important that work is done to give some partial numerical verification of it. So, this is the same definition you see in every textbook everywhere in the world. For the real part of S, bigger than 1, S is some complex variable, sigma plus IT. I define the zeta function by this Dirichlet series. I can also define it as this infinite product, the Euler product. And why can I do that? Well, if I expand everything and I'm not too worried about convergence, well, every term on the left appears on the right because of the fundamental theorem of arithmetic. Okay, so we've all seen that before. That's how you define the Riemann zeta function when the real part of S is bigger than 1. Now, the reason it's called the Riemann zeta function and not, say, the Euler zeta function, even though Euler considered it, is that Riemann took it away from S being a real variable bigger than 1 and converted it to a complex variable almost everywhere. So you can extend this definition analytically or meromorphically, if you like, to almost the entire complex plane. So the Dirichlet series up here doesn't make any sense when the real part of S is less than or equal to 1. Nevertheless, using the power of complex analysis, you can still extend it to almost everywhere. What do I mean by almost everywhere? Everywhere except that point where I put a cross there. That's a pole at S equals 1. This diagram I'm going to draw again and again throughout the talk of sigma on the horizontal real axis and T on the vertical real axis. Vertical imaginary axis, I'm sorry. So what have I said here? Let's pause that. I've said this product here says no zeros. Now, what do I mean by that? Well, if I give you a product of 10 things and none of those things is 0, then the product can't be 0. And you might say, that's great. We weren't all born yesterday. This is an infinite product. You have to be careful. Yeah, you do have to be careful about convergence. But roughly speaking, each of these terms in here is non-zero. Therefore, with a bit of hocus pocus, the product is non-zero. So because I can write this as a product of non-zero things, that says that in this region, the real part of S bigger than 1, there can be no zeros for the Riemann zeta function. So you get that more or less for free. And I'm a very old-fashioned, lazy fellow. I think if you can get stuff for free, you're on to a good start. So right off the bat, we have no zeros to the right of sigma equals 1. Now, I'm not going to write down what this thing is. And the past version of Tim, I assume he knew what he was doing when he wrote this. He'll move the thing up and down as time permits. So if I tell you there's no zeros out here, I can also tell you there's a functional equation. What does that do? Don't worry what it is. It relates points of zeta of s to values of zeta of 1 minus s. So if I know how zeta of s behaves, I know how zeta of 1 minus s behaves. They're not equal, but they're related quite well. So if there's no zeros out here, that means via the functional equation, there's no zeros over here. So this is good. We're off to a good start. For free, we got things out here, no zeros, almost for free via the functional equation, no zeros out there. That means everything else has to be in the middle. I mean, there's a thing in logic, isn't it? Like the law of the excluded middle, something like that. It can't be this way. It can't be that way. They've all got to be in the middle. So we're going to call this region, this is the region of interest. Sometimes people call it the critical strip. It doesn't really matter what you call it, but for the rest of the talk, we're only interested in what's happening in there. Oh, I should say, what have I done here? I've said no zeros, but just so that, you know, no one sues me for defamation. Yeah, sure, there are some zeros. We call them the trivial zeros, so -2, -4, -6. Yeah, there's zeros, and it's kind of interesting to look at those. They arise because of Bernoulli numbers, and we can take the Taylor expansion and see very interesting things about them. But for the purpose of this talk, they have no information. There's no information embodied in them about the primes, so we're not interested in them. So all other zeros lie in that critical strip, and that's where we'll be focusing on this talk today. All right, so I'm tapping at 1. It's unclear what the past version of Tim meant when he taps at 1. I could mean that I'm starting in the traditional fashion, in ascending numerical order. It's entirely possible. That's what I thought when I was tapping. So with an underline, so you know it's going to be important. So if rho is a non-trivial zero, whenever I say 0 for the rest of the talk, I'm in a non-trivial 0, so one of those in the strip. So if rho is a non-trivial 0 of the zeta function, then I can write rho as a real part beta, imaginary part gamma. And because it's got to be in the strip, beta has to be between 0 and 1. So in fact, let's just slow down here. In fact, oh, my hand is in the way, how terrible. In fact, the prime number theorem, which tells you asymptotically how many primes are up to a certain height, the prime number theorem actually shows you not only is beta in this closed interval, it's actually in this open interval. Or, put another way, you can't have beta, a real part of 0, being 0, nor can it be equal to 1. And in fact, this little line here is an equivalence. You could go both ways. We don't need that for this talk, but it's kind of historically interesting. So we have this, all the zeros are in this region, and in fact, we can say there's none on the 1 line, none on the 0 line. That's because of the prime number theorem. And there's some degrees of symmetry. They're symmetric about the line sigma equals 1/2 and symmetric about the line t equals 0. So there's no need for us to consider what's happening when the imaginary part, this gamma, is less than 0. It's a kind of a waste of time. Whatever's happening upstairs is equivalent to what's happening downstairs. So here's this diagram. I've only got one diagram. You know, it just comes again and again in every talk I do. So here's an attempt to say, can I get that out of the way? Yes. Success. Here's an attempt to say what's happening. If I have a 0 here, well, there's those 2 degrees of symmetry I was talking about. A 0 here means a 0 at 1 minus that point, which is down there. And then because everything's symmetric above and below the axis, I get a 0 here and I get a 0 down here. So I get 4 for the price of 1. 1 0 here generates 4. Likewise, 1 0 here on sigma equals 1/2 generates 1 downstairs. But I'm not going to consider what happens when t is less than 0. Everything's important. There's no extra information there. So we're only going to consider non-trivial zeros, and we're only going to consider the real part bigger than 0. Okay, so now's the time. What is the Riemann hypothesis? Well, I told you they were all symmetric. All the zeros were symmetric about sigma equals 1/2. Well, in some sense, the best possible way then is if they're all on sigma equals 1/2. And we'll get to what that means about best possible. But the Riemann hypothesis in one sentence is all the zeros, and remember I mean non-trivial zeros, all the zeros are on sigma equals 1/2. So all rho are written as 1/2 plus I times gamma. So I claim here that the Riemann hypothesis is important. Not only do I do that, but I put 2 exclamation marks after it. So you know it must be true. And I think I might be trying to make a joke by writing that's a small margin on the side of the page, possibly too small for me to prove, I don't know, Fermat's last theorem or even the Riemann hypothesis in this talk. So why is it important? Well, that's a good question. Everyone says it's important. Why is it important? Well, it's important for all manner of reasons, but I'm just going to focus on this talk about the distribution of primes. So what do I say here? Distribution of primes and other things, right? We can talk about other things. We'd have a whole seminar series about what these other things are. But if we just focus ourselves on primes, then the Riemann hypothesis is exceptionally important. So whether the zeros all lie on sigma equals a half, or how far they are away from sigma equals a half, those questions are intimately connected with how primes are distributed. So what do I say here? The distribution of primes and some other stuff is related to the largest real part of the zero. So here's an example. What do I mean by largest real part of a zero? I mean, if there are zeros really, really close to sigma equals 1, then we're in trouble. Then we're going to get bankrupted in what we try to do. That's the worst universe to live in, if there are zeros very close to sigma equals 1. If there are some zeros, but they're, sigma equals 0.6 or something, that's not too bad. The best thing we can hope for is that they're all on sigma equals a half. That's the best distribution we can hope for. So if one takes away nothing else from this talk, zeros near sigma equals 1 are terrible. Zeros on sigma equals half, they're the ones you want. So here's an example, the prime counting function pi of x. I alluded to it before when I mentioned the prime number theorem. What does it count? It counts the number of primes up to x. So how many primes up to 10? Well, 2, 3, 5, and 7 are primes. Pi of 10 is 4. Well, we know that pi of x is asymptotic to this logarithmic integral, which is roughly asymptotic to x over log x. Let's see if I can move that out of the way again. There we go. So this logarithmic integral here, dt over log t. If you integrate by parts, you give that to a first-year university student. You integrate by parts, the first term that pops out is x over log x. That's why it's written in this way. And just in case I forgot to mention it earlier, throughout the talk, if ever I write this tilde, this little twiddle, that is my, not just my, but it's the kind of standard shorthand notation for asymptotically equal to. That means this side divided by this side. Well, a bit tough to talk about sides, and there's 3 things. It means that A is asymptotic to B if A divided by B tends to 1. So x squared plus x is asymptotic to x squared, say. So if I know that pi of x is asymptotic to li of x, their ratio approaches 1, I could ask sensible questions about pi of x take li of x. Remember before I said x squared plus x is asymptotic to x squared? Well, that's true, but one of them, namely x squared plus x, is always bigger than x squared. So I could ask reasonable questions about the difference between 2 asymptotically equal functions. So I'm telling you this, you just have to take it on faith for now. I'm telling you that the error, the discrepancy, if you like, between the actual number and its main term depends directly on the zeros. So if all you're interested in is counting primes, then you're absolutely interested in where the zeros of the Riemann zeta function are. I wish there were another way. I wish there was some way we could count primes without that. I just don't know of any other way. So if what you want to know is the distribution of primes, then absolutely what you want to know is how the zeros, and if you like more specifically, how the real part of the zeros is distributed. I seem to be playing a kind of table tennis game with this little counter. I'll take it down to the bottom for now. So pi of x, as I say, is asymptotic to li of x. Now, what does the Riemann hypothesis tell you? It tells you that that difference is small. It's big O of x to the half plus epsilon. Just slow down. Past him must have had a couple of cups of tea that day. He's writing really quickly. So what does this mean? A standard kind of big O notation. This side divided by this side is bounded by a constant. That's all that means. So if we don't care what the constant is, then maybe the constant in here is 1,000. Maybe we don't care. And this is true for any positive epsilon. So think of your favorite small positive epsilon, like 1 over 100, say. Well, the Riemann hypothesis tells you that this side is less than a constant times x to the half plus 1 over 100, say. So the Riemann hypothesis says that you get a pretty good error term, about a square root. Remember, this guy is going like x over log x. So this is roughly the square root of the main term. That's a pretty good go. So if the Riemann hypothesis is true, you get roughly a square root of the main term as your error term. If the Riemann hypothesis is false, okay, I don't want to live in a world where the Riemann hypothesis is false, but let's just say it is false. What does that mean? Well, by definition, the Riemann hypothesis being false means that there's some zero with real part theta bigger than a half, like pick your favorite number bigger than a half and less than 1, like 0.7 or something. So there's some zero with real part bigger than a half, and this thing gets big. Let's not worry about what this symbol means. This side gets big. Pi of x take li of x is huge. So what this actually means is that this side divided by this side doesn't tend to 0. So, or in other words, this side is not smaller than x to the theta, say. So if you have some real part, or some zero with real part 0.7, then this difference is massive. It goes roughly like x to the 0.7, say. So the Riemann hypothesis gives you a very, very good error term. Riemann hypothesis false gives you a horrible error term. So what do I say here? We want the real parts of the zeros to be as small as possible. If they were all less than 0.6, great. If they were all less than 0.55, even better. But the best we can possibly hope for is that they're all on the line sigma equals a half. And as I write down here, you can't have zeros with real part less than a half because of the functional equation. Remember I said you had these degrees of symmetry. If I have a zero at, say, real part 0.9, then I have one at real part 0.1. So if I take it at 0.9 and get it closer and closer and closer to a half, I get it to be a half, sure, but if I try to push it a little bit further to, say, 0.4, then one pops out on the other side at 0.6. So it doesn't matter how clever you are, the best you can do is to push those zeros together until they sort of sit on the line sigma equals a half. So what this slide is trying to show is that in a very vague, well, I don't think it's that vague, but in a sort of hand-wavy sense, the zeros lying on the half line is the best you could hope for, and that's therefore the best case scenario for the distribution of primes. I think I tried to summarize this in a sentence. One of the advantages of giving a talk after you've recorded is that you can have a quick cup of tea while the past incarnation of yourself gets on with the business. So the real parts at sigma equals a half are in some sense optimal. Therefore, in a sense, the Riemann hypothesis is optimal. So it's not for me to tell you what to ask questions on, but if you were desperately looking for a question, well, here's something we could come back to if there were time. So you could come back and say, oh, it's on slide 3, and I've said optimal with inverted commas. And this PCC means the pair correlation conjecture. And we could talk, if there's time, about this real part here, not quite being optimal, but being sort of almost optimal. But there are other things we could consider. So let's get back to the main deal now. Between you and me, we're all friends now. It may as well be the case that sigma equals a half, real part being a half, is optimal. So this is my attempt to say that the Riemann hypothesis is important. And if we can't agree on it's important, well, I've done a pretty lousy job. Right, so what have I written here? It's important, and also there are 10 to the 6 reasons for studying it. You know, there's this Clay Institute of Mathematics put out these millennium problems. I don't really know what they are, but one of them is on the Riemann hypothesis. So if you solve that, you get $1 million US, which is, I guess, better than nothing. So, right, that's some motivation as to why you want to solve it. But we could have a whole lecture series about the implications for other areas of mathematics, but that's a start of why you'd be interested in it. So sometimes in the literature, many expository accounts start with why the Riemann hypothesis is important, but then sometimes fail, in my mind, to go the next step and to say, well, what if we don't know the Riemann hypothesis, but we know a partial version of the Riemann hypothesis? I guess what I'm trying to get at here is, if we know Riemann hypothesis, then good things happen. Well, what if we almost know the Riemann hypothesis? I mean, I'm being deliberately vague. If we almost know the Riemann hypothesis, well, can reasonably good things happen? You know, if the Riemann hypothesis is true, it's a great world to live in. If the Riemann hypothesis is close to being true, maybe we can deduce it's a good world to live in. Maybe not a great world, but a good world. So that's, I think, where some expository accounts perhaps don't go the whole distance. So what I'm trying to impress upon you here is, even if you don't know the Riemann hypothesis, you can still extract a lot of information if you know something that's close. We'll come back to what that means, close to proving the Riemann hypothesis. So I say here, knowing the Riemann hypothesis up to some x, and you may as well think of x as large, like, you know, 10 to the 10 or something. Knowing Riemann hypothesis true up to some large height is a good second best. I mean, I'd love it if someone proved the Riemann hypothesis. I'm still under 40, so if someone proves the Riemann hypothesis, we'll co-author the paper and I'm happy to share the Fields Medal, that's fine. But if we can't prove the Riemann hypothesis, well, what can we do? Let's not just say, oh, it's a nice pipe dream, but let's not worry about it. What can we actually practically do? So a good second best if we know it up to some large height. The larger the better. So the larger the height is, the better your results happen to be. And the link between how large that height is, so the Riemann hypothesis up to the height 10 to the 1,000. Well, that's better than up to the height 10 to the 10. But so what? You know, what good can we put that to work? How can we use that? That's what I want to focus on this middle section of the talk, is what we can use these partial verifications for. So why? A very kind of Socratic question. Okay, I've just told you some random fact which may or may not be true, and then I've asked why. Well, what a clever question. Why don't I try to answer that? So the main thing we need to do is to connect somehow zeros of the zeta function with prime numbers. If we can't do that, we may as well take our bat and ball and go home. I keep telling you that it's important somehow to connect the Riemann zeta function and primes. Well, how do you do that? Well, this is one of the Chebyshev functions. This is psi of x. It's a double sum. It's a sum over prime powers p to the m up to x. So the way that certainly I interpret this is when m is 1, it's a sum for p up to x, and I'm counting log p. Then when m is 2, I'm counting p squared up to x, or if you like, p up to the square root of x. So primes up to the square root of x with weight log p. When m is 3, I'm counting primes up to the cube root of log x, the cube root of x, and so on. Has to stop at some point, because when m is very large, x to the 1 over m is less than 2, and there's no primes less than 2. So this is well defined. It's a double sum, but sometimes written in this single way. And sometimes we write it, this is just some arithmetic function called the von Mangold function. We don't really have to worry about it. But for those who have seen it, that's the other way of writing it. It's just a compact way of saying lambda of n is log p if p is a prime power and 0 otherwise. So what's the prime number theorem? The prime number theorem you can write in about 1,000 different ways. So I said before, the prime number theorem really is about pi of x number of primes. Well, it's the same sort of thing. If I can tell you how the primes behave, I should be able to tell you how the sums of log primes behave, just by partial summation, say. So the prime number theorem in a different format is the same statement as saying that psi of x is asymptotic to x. So that is the essence of that. That is what the prime number theorem is. So what do we know? We know that psi of x goes like x plus some other stuff. Well, that's a good start. What's the other stuff? So psi of x goes like x plus some sum plus some error. So when you see ext, it's just an error term. Just don't worry about it. You know, we could write it down. We could spend some time. It's interesting, but not for the purposes of this talk. So how do I interpret this? Psi of x goes like x. Well, it's a very small error term that don't worry about. And this is the interesting thing here. This is a sum over x to the rho over rho, where rho is the zeros, beta plus I gamma. Now, I don't sum over all the zeros, otherwise the sum doesn't converge. So I sum up to some large height, some large t. These gammas go up to t, okay, between minus t and t, but it doesn't really matter. Goes up to height t. The gammas go up to t, and then I get some error term as a function of t. I mean, if t appears here and doesn't appear here, it should appear in the error term. I mean, this side here is independent of t. So if I take more and more terms, then this error term gets smaller and smaller, as I've written down here. So don't worry about the error term. This is a thing to worry about. How does this sum over the zeta zeros behave? I've said psi of x is asymptotic to x, so that should mean that this side divided by that side tends to 1. That should mean this side divided by this side tends to 1. Or, another way, the whole thing divided by x, there's your 1 right there. It means this thing, when divided by x, should tend to 0. That's what the prime number theorem is saying when I recast it like this. This term here, divided by x, should tend to 0 as x tends to infinity. So, okay, I say we know. Look, again, we can have a whole lecture series about how we prove that. But okay, that's the equation that we know, which Riemann conjectured and von Mangold proved in 1905. Right, so I'm trying to impress upon you the importance of knowing the Riemann hypothesis up to some height. So if the Riemann hypothesis is true to height h, I should just say, I mean, I'm a very casual guy. I haven't actually told you what it means to be true up to height h. What I mean by that is that every rho equals beta plus I gamma, all the gammas up to h. So for all those zeros that lie between the real axis and the height h, all of those have real part a half. So every 0 in there is where it should be, namely on the critical line. So Riemann hypothesis true up to 50 means all the zeros with the imaginary part up to 50 lie on the critical line. So Riemann hypothesis true up to height h, then what? Well, then I can split this sum up into 2 chunks. One piece will be the gammas up to height h, and they'll have real part half, and then there'll be the gammas that are bigger than h, and they'll have real part whatever they have. So what that means, this real part 1/2 is in general much, much better than the real part I would otherwise have got. Remember, if I don't know anything about the 0, this real part here could be as big as 1 for all I know, or like 0.99. So if I know nothing about the real parts of the zeros and I want to bound this, I could use the absolute value, say. If I'm bounding this, that's x to the beta, the real part. And beta could be 0.999 for all I know. But here, what have I done? In this piece of the sum, I know the real part's 1/2, much, much smaller than what it could be in this part of the sum. So by splitting it up into 2 pieces, I'm making a huge saving in this part here. So I've written down here, I'm sorry, the writing's quite small. I think I'm just writing down what I'm saying. Oh, now I'm crossing it out, so don't even worry about it. So, and I've made a smiley face. It's unclear what that means, but I'm saying the terms here are much, much smaller than the terms over here. So I've made a saving. That's the point. I've made a saving by injecting into this proof, into this scheme, the idea of the Riemann hypothesis being true up to some height. So now I can just get my computer out and I can compute this. You give me an x, I can compute this quantity here, and now I can use some other analytic techniques for computing the tail piece of the sum. The important thing is I've taken one sum, split it into 2 parts, and made a huge saving on one of these parts. So why is the Riemann hypothesis good up to height h? Well, Riemann hypothesis is good all the time because it tells us the error term in the prime number theorem. Well, Riemann hypothesis true up to some height h gives us a pretty good prime number theorem in a certain range. So what's this diagram here saying? So we know the Riemann hypothesis up to height h. So all the zeros that you see are on the critical line. Okay, and now what happens after h? Well, they could be anywhere. Well, they can't quite be anywhere. We have results here called zero-free regions, saying there can be no zeros under here. They can't all, I mean, some of them could get very close to sigma equals 1, but they can't all get there too quickly. So we have a region here, which is kind of interesting. It's a topic for a different talk, but we have a region here where you can't have zeros. You could have zeros just outside that region, but you can't have any in here. Now, unfortunately, this region tends to sigma equals 1 when t tends to infinity. So at some point, it kind of ceases to have any use. But still, just knowing that, these kind of partial results gives you enough to get out very accurate information about the distribution of primes. So this quick summary of where we're up to now, just under halfway, just about halfway of the talk, I should think. A quick summary. When I say zeros, I mean non-trivial zeros. The zeros of the zeta function are very important for the distribution of primes. Zeros with large real parts are the worst. They're absolutely terrible. The best thing for us is zeros with small real parts, and the smallest they can be is sigma equals 1/2. Because sigma equals 1/2, you can't get any smaller than that. So the zeros with large parts are terrible. We want to make as many zeros as we can lie on the line sigma equals 1/2. So I'm trying now to give you 3 reasons. Excuse me. I suppose they're reasons. Well, point 1 I've written is the Riemann hypothesis is important. Well, I hope that I've made that somewhat clear, but again, we've plenty of time for questions later if people want to ask. A question at point 2, the Riemann hypothesis to height h, where h is large, is important. Now, I've tried to convince you that from the previous slide. I tried to give this argument that if we split the sum up into 2 bits, Riemann hypothesis true up to this height, and who knows there. Well, there's a huge improvement we can have here, so we improve the whole sum. That's where 2 is. And I presume this is 3. If I can count, this should be point 3. Oh, right. Yeah, this is an interesting one. The Riemann hypothesis to height h, not just that they lie where they should lie, but also I know exactly where they are. So I know that this one is at, the first one is at 14.1, whatever. That location is actually important as well. So why 3? I've given you nothing so far to imply why 3 is true. I've just told you the real part's important. So now I'm asking the question, the imaginary part is somehow important. And this sort of harks back to this question I planted in the audience a few slides ago about the pair correlation conjecture. I won't talk about that again now. We can talk about that in question time if people are interested or if there's time. So what I'm trying to say here is that if we know the location of the imaginary parts of the zeros, then we can rig the deck in such a way that we can make the terms reinforce each other. After all, what is this? X to the I gamma. It's E to the I gamma log x. So it's a complex exponential. This part here, some number, don't really care what it is, but this here is spinning around the unit circle. So sometimes it might be pointing this way, sometimes this way, sometimes this way, sometimes this way. Now, if I know where the gammas are, I can say, I want the term to be pointing that way. And I want the next term also to be pointing that way. And the next term also to be pointing that way. So if I know where the gammas are, I can choose an x using what simultaneous approximation, or what's it called, Dirichte's theorem. So I can choose an x cleverly to say x is such that I'm pointing that way on that zero, and on that zero, and on that zero, and on that zero, and so on. So one does this a lot when one wishes to point out things like large oscillations in sums, like to disprove the Merton's conjecture, if people have heard of that, or to disprove who knows what. So many times one deliberately takes advantage of the numerical location of the zeros. Right, so the trivial bound is to say I've got a complex exponentials, trivial bound that have modulus 1. So therefore the sum of them is at most a sum of ones in size. But I know that they're not just randomly spinning around. If I know the gammas, I can choose a series of x's very cleverly to make them either cancel out, have one pull this way and one this way, or have them reinforce. So I think this is my attempt to say it's very useful for things like disproving the Merton's conjecture, exhibiting biases and oscillations in certain sums. So this point 3 is interesting, and I talked about this in some other talks. It's not really the thrust of this talk, but this idea of not just knowing that the zeros lie on the sigma equals half line, but also knowing where they lie can be very useful. Now, what have I written here? It's also useful for passing the long winter evenings. Well, there you go. It's very cold in Canberra, it can get a bit dull. So if you know about this stuff, it's kind of interesting, I suppose. So I've tried to tell you why it's important. Okay, it's important, but also a partial verification is important. And to some extent, I've said the location of the zeros is important. So I've written there pause for questions, but just to keep to time, and Shanta was very kind to remind me of the format. Just to keep to time, we might push past this, and then if there's questions at the end, we can take them. So this more or less finishes the second part of the talk. The first part was the zeta function. This part was, it must have been cold when I was recording that, I was rubbing my hands. The first part was the introduction about the zeta function. The second part was why the Riemann hypothesis is important and why partial verifications are important. And this part here, I should think, is talking about the work that Dave and I did, which verifies numerically the Riemann hypothesis to a new record height. So I think I'm pointing here at 2 and 3, points 2 and 3, that Riemann hypothesis up to some height is very important, and also the location. Oh, I'll put this out of your way. So this is the state of play. This is where the field is up to at the moment. All right, so point 1, the Riemann hypothesis is still unsolved. At least it was unsolved when I wrote these notes a couple of months ago. Is it a shock? Maybe it is. So the Riemann hypothesis is unsolved. So therefore, as I tried to elucidate in the previous few slides, it's very important then to know the Riemann hypothesis up to a certain height. The higher the better. So Dave Platt in his thesis in 2011 and in the paper that came from that in 2017 proved the Riemann hypothesis up to 3 times 10 to the 10. And what does that mean again? That means every zero with imaginary part less than 3 times 10 to the 10 lies on the critical line. What he also did, Dave, in the same series of papers, not only did he prove the Riemann hypothesis up to that height, but he showed, well, let's not say exactly, but he showed each one of those zeros that lie on the line with an accuracy of, like 100 bits, say. There we go, isolated to 100 bits. As an aside, we can come back to this for questions maybe, but it's very interesting. One never finds a zero of a zeta function. All one ever does is say it lies in that interval, and then you can make that interval smaller and smaller. And there's no closed form known for a single zero. I mean, presumably they're all transcendental, but no one even knows whether they're irrational. So no one knows anything. So what Dave did was he proved the Riemann hypothesis up to this height, and he isolated the zeros to a very high accuracy. So high, in fact, that I don't think there's going to be anyone in the next, 20 years who needs to know the zeros up to that height to a higher degree of precision. I just can't imagine there being any project happening in the next 20 years that would require this step of the proof to be improved. So, okay, what did I do? Oh, I guess jocularly I say I tried to prove the Riemann hypothesis, but it was too hard. Oh, well, that's modesty for you. 3, I make a point about 3. I think this is enough for everything, and I really do think that's true. I'm not a computational expert, but I can't see anything in the literature mathematically that would require one to have such good precision or better precision. So yeah, I think that you could rerun the calculation to 1,000 bits. It'll take you an awful lot of time, but I just don't see that that's useful at all. So what Dave and I proposed to do was to improve his algorithm, but to forget about actually finding the zeros. So when we did our computation, the reason we were able to get so high was that we didn't really care exactly where the zeros were so long as they were on the half line. So we didn't bother to record the fact that there's one here and there's one here. What we just wanted to do was to say, look, they're there somewhere and we found them all. They're in some range. Okay, we found them all. We'll move on. So that speeds things up immensely. So what do I write down here? Why do any of this? So why do this? Well, it improves other results. Okay, that's a reason. George Mallory, the mountaineer, said, okay, well, why do you climb Mount Everest? Because it's there. It's got something to do. Maybe the Trudgian version is because there's bills to pay. I've got a family to feed. I've got to do something to earn my money. So you've got to solve some problems, say. But also, there's quite a lot of confusion abounding in the literature about the Riemann hypothesis and the height to which it's proved, which I found quite odd given the central place it ought to have in sort of analytical and computational number theory. It should be a thing. The Riemann hypothesis is or is not proved to a certain height, and that shouldn't be a contestable statement. But what I hope to show on the other side is that there were lots of different claims going around, not many of which had been peer-reviewed, many of which seemed to have either glaring errors or just careless omissions. And so what other people say outside of number theory would do, they wouldn't know which of these theorems to quote, because there's 3 different ones claiming 3 different things. So we thought, well, 1, we'll go higher than other people, 1, because we can, 2, because we're going to sacrifice accuracy for extra height. We're not going to bother isolating the zeros because we don't need to. We just need to show they're there. And then 3, we're going to give some clarity so that if someone wants to point to a figure, they can say, definitely that's the figure. So the figure now is 3 times 10 to the 12. That's your other takeaway for the talk. If anyone asks, if someone stops you on the streets of Delhi and says, what's the height to which the Riemann hypothesis is known? You say, well, I was at a very interesting talk last night, and this fella from Canberra said 3 times 10 to the 12. So that's what I'm trying to illustrate here, that there is a figure, that's the figure to quote, and this is why we were interested in it. So I remember I gave Platt's figure. He proved the Riemann hypothesis up to 3 times 10 to the 10. So his figure is quoted by some people, and his figure is completely robust. He uses a very robust algorithm, which I don't think anyone disputes. I wrote a paper with him, but I certainly don't dispute it. So there's a couple of other results that float around. So there's one by Vitanivsky in 2004, which goes a little bit higher, and this was a computation spread over a wide cluster of computers. There's also a result by Gourdon in 2004, which goes up to 2 times 10 to the 12. There's also not a very well-known result by Franke, Berta, Klein-Jung, and Joost in 2017, which goes up to 10 to the 11. And you might say, well, these are all bigger than 10 to the 10. So, what's the problem? Well, some of these seem too good to be true. There's no details given for how they're doing it. There's an awful lot of zeros to compute. There's an awful lot of errors that can creep into the computation. So there's no details given whatever. They just said, oh, we just did it on the side. That might work, but how is that replicable? How is that? It's unclear to me that that's good enough. Also, 2 and 1 were never published, and it's unclear to me, not only were they not published, but it's unclear to me how on earth the errors, the error accumulation was handled in these problems. You're doing, let's not talk about the details, but you're doing a whole heap of fast Fourier transforms to speed up the process. You're hoping to find a whole bunch of zeros and then reconstructing a function based on its signal using, Shannon transforms or whatever. Okay, so when you do that, there's a whole lot of noise that can creep in. And And when you're doing this to that many zeros, it only takes a little bit for you to be out and the whole thing's gone. So without any details, with these almost too good to be true results, we were a bit skeptical, as indeed are many people in the community. So we thought, okay, well, we can do this. There are various theoretical goals that we can insert. There are various tricks we can use to speed things up. But what we wanted in a sentence was find a result that can be pointed to and people can say, that's the result. That's the height to which the Riemann hypothesis is proved. And it's being done using a robust algorithm, I was trying to invoke some authority here. So find an H that can be pointed to with certainty. So see Tau and Helfgott. So when Harold Helfgott proved the Ternary-Goldbach conjecture in 2013 or 14, I can't quite remember, he comes across this problem. He needs to quote a result. He needs the Riemann hypothesis true to some height and says, well, he ends up taking a result from the 80s up to 10 to the 9. And I'll quote my fellow Australian, Terry Tao. I think if you win a Fields medalist, people should listen to you. So Terry Tao also in his paper on an approximation of the Goldbach conjecture makes this point as well, that it's almost embarrassing that there's no definitive value that you can point to and say, that's it, the Riemann hypothesis is proved to that value, given that the Riemann hypothesis has such a widespread impact on the field. So, yeah, okay, I mean, every time I give a talk like this, someone says, okay, how certain can you be? The computer could have made a mistake. Yeah, I guess it could. So like any computer calculation, maybe there was a cosmic ray that came down and fried the chip. Well, there are ways you can try to account for that. There are random checks you can do. There are checksums you can do. But perhaps the best one is to try to use sometimes called ball arithmetic or interval arithmetic as opposed to floating point arithmetic. We're not going into the details now, but roughly speaking, interval arithmetic says the answer to whatever sum you're doing lies in there, and it remembers that. So then if you add this to something else that lies within there, then the new answer lies within here. It remembers that. So it doesn't have to worry about truncating things. It remembers intervals where the answers must lie. And so that means you avoid some of the problems with floating point arithmetic. So that's more or less what I wanted to talk about. There's some extra slides here, which I think we'll probably skip, just to make sure we finish with plenty of time.
Hello, Tim?
Yep.
Yeah, so there's one question.
Oh, I'm sorry.
Yeah, so what is the height of Odlis cos 10 power 21 zeros? There was a question from one of the participants.
Yeah, yep. Thank you. Yeah. So, if I understand the question correctly, so Andrew Odlyzko in the 80s, I think, computed a whole bunch of zeros of the zeta function. So there's two things you can do with the zeta function. You can compute all the zeros up to some height, or you can start at some other height and compute a bunch of zeros around there. So what Odlyzko did, he computed a whole bunch of zeros to a very high degree of accuracy, and they're on his website. I forget exactly how high he goes to. Maybe it's the first 1,000 zeros. Maybe they have 10,000 decimal places or something. But what he also does is then he says, well, now I'm going to go to some very large height. I forget what it is, maybe like 10 to the 30 or something. And I'm going to compute the first 1,000 zeros around this height 10 to the 30. So he's not proving the Riemann hypothesis up to 10 to the 30, but he's saying, let's see how a random packet of zeros behaves high up the critical line. And he was working on this pair correlation conjecture, which maybe I'll get to in the questions at the end. So I've given a classical, well, we're both from political cities, Delhi and Canberra. I've given a classical politician's answer to the question that I haven't answered it, but I hope that I've waved my hands around enough to convince you that we could talk about it some more if we needed to. Shall I keep going, Shanta? Or
yeah, please continue.
Okay, sure. Well, as I said, there's plenty more material, but I don't wish to speak for much longer because I want to make sure that we can ask questions, and I appreciate that online talks are tough because I can't see whether I can't see what you fellows are looking at, and I can't really judge the pace so well. So. Roughly speaking now, I'm just trying to give you a quick outline as to how we do this. I'm not going to go through the technical details, but remember I said before that no one knows where a zero is. You know, if someone says true or false, we know the exact location of a single non-trivial zero of the zeta function. Okay, the answer is false. We don't. The only thing one does, I mean, there could be some exotic method. I'm just not aware of it. But the thing that everyone has done since Riemann's time in the 1850s is to say, look, how do I find zeros of a complex function? That's difficult because I have to find, maybe I find the real part is close to zero here, the imaginary part is close to zero here. But it's no good if the real part's zero here and the imaginary part's zero there. You know, they have to be zero at the same point. They have to be coincident zeros. So that in general is quite difficult. So what you do is you convert the zeta function into, sometimes people call it the completed zeta function. Let's not worry about what that is exactly. Well, the point to take away is that this function here has zeros that are the exact same positions as the zeros of the zeta function. So we take the zeta function, it's got zeros somewhere. We convert it to a different function which has zeros in the same spot. And you might say, well, what was the point of that? Well, this completed zeta function happens to be real. So if it's real, then it's much, much easier to find where the zeros are. So in this little diagram here, I'm saying, let's look for zeros of this function. It's the same as zeros of the zeta function, but if we look for zeros of this function, what do we have to do? Well, let's measure it. Let's just compute it at this point. Suppose it's positive, okay? Let's compute it at this point. Suppose it's negative. So it's, you know, plus 1.1 here and it's minus 0.6 down here. Okay, well, the function's real, and I guess I should say it's continuous. So it's real and continuous, and we use the intermediate value theorem. I had to drum my fingers there because was it the intermediate value theorem or the mean value theorem? It's the intermediate value theorem. It's positive here, it's negative there, so it has to be zero somewhere. And that's it. That's the only way anyone tries to find a zero of the zeta function, is to take then tighter and tighter intervals. If it's positive here and negative here, it's a zero in there somewhere. Okay, well, maybe I get a smaller interval. I'll measure it here and I'll measure it there. If it's positive, well, can't deduce anything. Okay, but if I tried to measure it here and it was negative, all right, well, then there's a zero in there somewhere. And now I can try to bring this side of the interval in. So whenever anyone says about isolating a zero, they mean exactly that. Squeezing it in so it's in there somewhere. No one ever finds a zero. But by doing this, you convert a very difficult problem. I mean, in general, finding the zero of a complex function is not a trivial thing to do. You convert it into a straight up kind of first year calculus problem of finding something that's positive here, negative there, so therefore it has to be zero in between. All right, so I think I've made some comment, preferably to the Fields Committee, that I've illustrated a perfect application of the intermediate value theorem. So if that doesn't get me an invite to St. Petersburg, I don't think anything will. So what I'm going to do, just to stick to time here, I think after this little diagram, I might skip ahead. All right, so here's a quick example. This doesn't tell you anything more than what I just told you, except to say, suppose I measured it and it was positive here, negative, 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 positive. All I can deduce is that there's a zero in there and there's a zero in there. Now, there may have been more zeros. There's certainly one in there and there's certainly one in here. Now, there could be 1,000 in here that I've missed for all I know. So when we play these games, we acknowledge the fact that we could have missed some zeros. So part of the trick, part of the computational trick, so yes, so I'm saying the function could have done something like this. Could have actually been 2 zeros in there. I mean, it's pretty easy to show there has to be an even number of zeros in there, 0 or 2 or 4 or 6 or so on, but I could have missed 2. So we have to be very careful. On the one hand, we want to measure this completed zeta function a lot. The more the merrier. Because each time we measure it, that's the same as saying I'm taking a point that's either positive or negative. All right. The more of those, the merrier. If I had measured this at this point, 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 then I would have found those 2 zeros. So if I measure it in a very, very fine mesh, I've got an excellent chance of finding zeros. But then it's a lot of computations to do. It's an awful lot of computations to put down, 10 to the 20 different points and compute all of those. You can forget it. So, well, conversely, we could only measure it at a few places. But then we run into the trouble like this, that we may have missed 1,000 zeros. It could have been 500 in here that we just missed. So there's a trade-off between how many computations you want to do and how fine a mesh you want to do. And the cleverness of this fast Fourier transform, or this windowed algorithm that was pioneered to some extent by Andy Booker, who was Dave Platt's PhD supervisor. This idea is to say, well, if we want to find 1,000 zeros, let's not put down 1,000 points. Let's try to get away with 10 points. And if we put 10 points down, we might be lucky, we might pick some zeros. But if we miss some, we hope to be able to reconstruct the function somehow, because we know the, what's the phrase? The function is band limited. The function's Fourier transform have compact support. That means it can't be doing wild things between zeros. So it's not quite cheating, it almost is, but you're putting down deliberately few points, less than you think you'll need. But even if you miss some zeros, you can, if you like, you have enough of a skeletal diagram of the function that you can build back, put the flesh back on the bones and reconstruct the function from that. And it's exactly that kind of saving time. If you want to find 10 to the 10 zeros, 10 to the 10 points might do it, but it might not do it. There's also a lot of things to compute. So put down fewer points and then use this kind of Fourier transform algorithm to try to reconstruct the algorithm. And it's for that reason that we're able to go so much higher than, say, computations done in the 90s, in the 2000s. And the reason we're able to go even higher than Dave's computation, okay, we ran the computation for a very long time, but also we sacrificed the accuracy. We didn't try to, remember this diagram here? I could say, okay, there's a zero in there, but the size of this interval is, I don't know, like 0.6 or something. I want it smaller. So I could not waste time, but I could invest time into making this interval smaller and smaller and saying, I can guarantee there's one in that very small interval. We didn't do that. We just said, yes, there's a zero there, let's move on. And there's another technique, which I won't talk about now, another technique where you can say, you can guarantee that you haven't missed zeros. You found 10 zeros, well, there could be others. There could be others out there that you just missed. Well, there's a little test you could run. It's called Turing's method, so named after Alan Turing. You can run Turing's method to test at very little extra computational cost that, yes, I can confirm you found all the zeros in this region. So what we do, we look for sign changes. We then try to reconstruct as much of the function as we can. Then we apply Turing's method to test, have we in fact missed any zeros in this region? If the answer is yes, okay, we go back and we put some more points down. And then reconstruct it again. Have we found the right number of zeros? Ask Turing's test. If the answer is yes, we have, great. Then in that interval, not only is the Riemann hypothesis true, but we found all the zeros we're supposed to have found. We haven't missed some random ones somewhere. So this process is, well, I think this is a process that people could, well, as I say, Dave handles the computational aspects of this. I mean, I deliberately put more material in this talk just in case we did it slightly differently. I guess the last slide that I wanted to talk about was this one. We used an awful lot of resources for this. So roughly 850 core years on a very fast supercomputer. You know, like there's, you know, IPL rankings or whatever, you know, university rankings. There's also supercomputer rankings. So apparently this is the 47th fastest supercomputer in the world. I mean, if you believe that, you believe anything, but that's what they tell me. So it's a very fast computer, supercomputer arrangement here in Canberra. So we use an awful lot of time on there, much more than what Dave used in his thesis. And the end result is this. Okay, well, you don't have to read that number off exactly. I'll just tell you it's 3 times 10 to the 12, a little bit bigger. And another number that is quotable, I suppose, is that the first 10 to the 13 zeros, or 1.236 times 10 to the 13 zeros, lie critical line. So yeah, the main takeaway is that using a combination, there's some theoretical aspects, some sort of analytic number theory aspects, which we could use as well, and we did, but I'm not going to talk about them now. So yeah, and finally, I guess in terms of, oh, it's a bit dark. You know, just like with a talk, you've got to figure out when to stop, and I'm going to stop in about 30 seconds or so. But we're trying to think, what height can we get to? You know, maybe we could get to pi times 10 to the 12, because it could be interesting. I mean, if people have to cite this result, then they have to cite it as pi by 10 to the 12. But we had run the computation for so long it was 850 core years, and it felt like 850 human years. It was so long, and it was so painful to update it each time, not just to debug stuff, but to update it, to put in new theoretical estimates and so on. Then in the end, we just said, look, we're done. So the paper is submitted. It's on the archive. I don't know when it will be, when we'll receive a referee's report, but the quick kind of one-line summary is that the Riemann hypothesis is true up to a little bit higher than 3 by 10 to the 12. You can see this paper on the archive. I think I put it down here. Oh, right, I talk about some instant wins. Let's not worry about that. Right, so there's the paper. The Riemann hypothesis is true up to this height. It's on the archive, and I say something like, well, if you have any questions, ask Dave Platt. Dave Platt answers questions very well and is the computational genius behind this work that we do. It was quite fun to work on it, and also quite fun to trace, and I didn't talk about it today because it wasn't much time, but to trace what you get for free. If you prove this Riemann hypothesis to a certain height, then there's half a dozen results that you get. You have to work a little bit on them, but you get those results much more easily than you got them earlier. So you really do add to the pool of knowledge. So thank you very much. I don't know about whether I should unshare my screen, but thank you very much for your attention, and I'm happy to take any questions.
Yeah. So Tim, thank you. So there's a number of questions. So maybe I'll first read out some questions. So, does your method tell if the zeros are simple? So that's one question. And is the set of zeros discrete? That's another question. So that's a.
For the first question, yes, the zeros are simple. So the conjecture, I mean, the Riemann hypothesis is a conjecture. We also conjecture that all the zeros are simple. There's not a huge amount of reason for why that's true. We could talk about why we'd like it to be true, but there's not a huge amount of evidence for that. But yeah, I think everyone thinks a zero should be simple. I certainly do. So when we use this method, we are only looking for sign changes. And so if there's a zero of multiplicity 2, say, we're not going to detect it. We could run the algorithm for 1,000,000 years and we're not going to detect it. So that tells you that the only zeros we're ever going to detect are zeros of odd multiplicity. And in fact, we can show that we have isolated them enough to show that they are in fact simple. So we haven't isolated them to within 100 bits, but enough to say, yes, there's a zero there, yes, there's a zero there, yes, there's a zero there. So yes, our method is computing simple zeros. I should also add, our method doesn't say anything about zeros off the line, except that there are none in this range. I mean, suppose we ran this algorithm up to 10 to the 50, and suppose there were loads of zeros off the line. Well, our method's not going to find them. Our method's just going to return fail. It's going to say, I think I found all the zeros. I'll apply Turing's method. No, I've missed some. Okay, I'll go back. I'll sample the function more. I think I've got them all now. No, I've missed some. You're just going to stick in that loop. We're only looking at things on the critical line. So there's nothing this algorithm can say about the possible location of zeros off the critical line. So I think and that's something we addressed in the paper. I think that's something that's worth pointing out. So the second question, this is partly my, I don't know about my lack of education in the finer points of mathematics, but I must say I'm not quite sure what the question means when they say, is the set of zeros discrete? I wonder, I don't know who asked the question, but is whoever able to ask the question either in the chat or verbally or via Shunter, just to help me out with that. I'm happy to discuss it, but I don't quite understand.
Okay, what I mean is, do they have a limit point? Like in an interval, are there infinitely many zeros? Can you hear?
Yes, yeah. Yes. Sorry, yes, I can hear you. So,
Tim, I think I also had the same question that Riddhi asked. I think this is Kaushik, and yeah, I think I had the same question too.
Oh, right. Well, but before I try to answer it, I might have to ask for sort of an explanation of I'm sure your explanation is perfectly sound. I just don't quite understand. So say I ask for an interval, so between t and t plus delta or something. I can tell you, roughly speaking, how many zeros will be in that interval, and it will depend on t and it'll depend on delta. So another way to look at it, between say t and 2 times t, there's roughly t log t zeros in there. So in any interval of a I don't want to say a fixed width, but you give me an interval of a certain width and I'll tell you how many zeros are in the critical strip in that width. I can't tell you how many are on the critical line. I can't tell you how many are on sigma equals a half, but I can tell you how many there are in that strip. So yes, if you give me t and t plus 1, say, or nothing special about 1, t and t plus 10, then there's roughly going to be log t zeros in that interval. And that's true for all t. So yeah, if you pick a favorite t, like 10 to the 1,000, then there's roughly log of 10 to the 1,000 zeros between that height and that plus 1. So I don't know whether that answers your question, but
okay, then it would mean it is discrete. So
okay.
It is finite, then it's discrete.
Yeah. So yeah, in any interval, yeah, we know the number of zeros in an interval roughly. That's an interesting question on the side as to how can we make that estimation better, and that itself is contingent in some roundabout, not quite circular way, but that's contingent also on the Riemann hypothesis. But I can tell you how many zeros are in the strip, and then of course, well, who knows how many are on the line. I should say I didn't talk about it in the talk. Again, one could give a series of lectures on the zeta function and the zeros, but another way of saying that we're close, if you like, to proving the Riemann hypothesis is to say something like, well, yeah, there could be some zeros off the line, but if I look at all the zeros in the box up to height t, where t is very large, then at least 40% of those lie on the critical line. So look at all the zeros in a box up to height t. Now look at all the zeros on the critical line up to height t. Divide the first quantity by the second quantity, so the percentage of zeros up to height t that lie on the critical line, and that number is bounded below by 0.4 as t tends to infinity. And maybe I'm a bit off, maybe it's like 40.1 or 41.1 or something. It's a number around 40. Yes. So yeah, that's also a result. And it's kind of interesting to see, well, why is the number so low? How can one improve that? So sometimes that's also quoted as saying, you know, at least % of zeros lie on the critical line. And we know that at least 40% of zeros are simple. So whatever the quantity is for lying on the critical line, the fraction is slightly less of those that we know are simple. And there's some interesting reasons why that's true, but we have these two kind of results, like at least 41% of zeros are on the line and at least 40% of zeros are simple, say. So that's an interesting aspect as well.
Hi, Tim. This is Kaushik. Do you?
Kaushik, yeah, I think you wanted to ask something.
Yeah. Tim, sorry, sorry if this is a very naive question, and you could totally say go read your paper, and I could do that. But I'm kind of confused when you say you know roughly this many zeros in a given interval, and yet you're am I misunderstanding, or are you saying yet you've verified the Riemannian hypothesis up to 10 to the 12, about 10 to the 12? So it's not, that's why I was wondering if I gave you an interval, would you know like exactly how many zeros are there in that on the critical line? And then you can say like, okay, I've checked all these zeros indeed. I've counted, like I knew a priori how many they are going to be. So I've done, you run your algorithm or yours and Platt's algorithm, and you've figured out that all of those, you've found that this many zeros are there and they all lie on the line. Sorry.
Yeah, no, that's a very good question, and I think that I may have perhaps misled people when I used the adverb roughly. I think so. The short answer is yes. We know in a given interval that all the zeros that ought to be there are on the critical line. I guess when I said roughly, what I sort of it's certainly my fault. What I had meant to say is that. We will make a first approximation. We'll take an interval and we'll see how many zeros we can find in one go. So we'll put down a whole bunch of sampling points. We'll measure this completed zeta function here and here and here and here and here. And we'll look for sign changes. And we'll hope that we're putting them down sufficiently frequently and in a sufficiently clever location that on doing that, giving an interval, putting down these points, measuring, and using the intermediate value theorem, we hope that that will capture roughly the right number of zeros. So maybe 90% of the zeros in there. So we hope that on the first pass, we can get as many as we can. And actually, on the first pass in the algorithm, we get close to 99% of the zeros that are there. We get them on the first go. So it's not quite luck. I mean, you kind of make your own luck, but but partly luck, part by design. So on one application, we get roughly, meaning not quite, but almost the right number of zeros in the interval. And then we go to Turing's algorithm, to Turing's method, and say, did we get it right? Yes or no? And he comes back and says, no, you've missed 4, say. Then we go, okay, well, now we're going to have to put some more points down, and now we found those 4. So now we have exactly the right number of zeros. So the first time round, we didn't get it exactly, but we got it close. So maybe roughly was a poor word. We get almost the right number, but sometimes we have to run the algorithm again and again. Very rarely more than 3 times, almost never more than 3 times. But sorry, that's what I meant when I said roughly the right number. So yes, I can say in any given interval, I will find, presuming the Riemann hypothesis is correct, because if it's not correct, I'm never going to find the zeros off the line. But if the Riemann hypothesis is correct in this interval, then yes, I will run the algorithm long enough and I'll find all the zeros. Yeah.
Yeah. So first, let's thank Tim, and then after that we ask questions. So all of us can please clap. I mean, unmute yourself and clap.
Thank you.
So now Matthew can ask questions.
Hi everyone. Hi Tim.
Hi, Mateo.
Time no see.
Exactly.
So, after all these technical questions, I had 2 questions about more mathematical gossip. You spoke about these 850 transcendental years in computation, but in real life, do you have an estimation of how many days, weeks took?
So yeah, the short answer is no. I don't. Well. I guess we started running the computation in. We got the grant in 2015, and so we started running it in early 2016 and stopped running it at the start of this year. Now, we weren't running it for 4 solid years, but we would run it to a certain point, then stop, and retweak it, put some more mathematics into it, run it again. But I think the earliest computation was in early 2016 and the latest one in this year. So 4 human years where something was running in the background. I don't have, it's possibly in the paper, but I don't have at the top of my head how many actual human hours the machines were running for. But yeah, sort of 4 years of my life was how long.
And do you think there is like someone else use more hours, like second gossip,
I mean,
mathematical gossip?
Yeah, probably. I mean, sure. Anyone could, and I guess if someone wants to, that's great. If they want to do that, that's okay. I guess. Well, what I would love is for someone to be motivated to improve on this result, and instead to come up with a better way of doing it. If someone could come up with a better way of doing it and prove the Riemann hypothesis to 10 to the 20, that'd be great. Now, I don't mind if no one looks at our method again. I guess partly what we wanted to show is that it's very hard. We went 2 full orders of magnitude higher than Dave's, but we had to spend a huge amount of resources on it. So if you like, yes, you could instead of 850 core hours, someone could run it on 1,000 core hours and go a bit higher. That's fine. Unclear to me what benefit that serves to humanity, but one could do that. But partly the reason is to say, it's difficult to improve on this result just by running it slightly longer. If you want to get to 10 to the 20, you can forget it. as in.
But yeah, but I meant like maybe it's like, is this in number theory the paper in which were used more computational hours in general? Like
Oh, no, I don't. I mean, so that's a that's a good question. Whether can I name another number theory paper that used more core hours? I don't know. I'm sure there must be. Certainly, it's the longest computation that Dave's worked on. I mean, I've only worked on a handful, so my opinion doesn't really matter. But for Dave and the people around him who helped him implement the code, it was the longest by a long shot, by at least a factor of 5, say. So, yeah, I mean, with probability 1, it'll be the longest computation I will work on forever. Maybe I'm in mathematics for another 50 years, but I think that's the longest computation that I want to work on.
Thank you.
I think Sneha had some question. Sneha?
Yeah, hi. Yeah, so since we were already at some point like discussing about the percentage of zeros and so on. So,
oh yeah.
Yeah, so just like Selberg's and Levinson's methods on percentage of zeros for Riemann Zeta can be like used and has been used for like several other combinations of derivatives and like for many other L functions. So like, do you see, so of course I can go read the paper, but like, do you see the method also like working for some other, like verifying the Riemann hypothesis up to a certain height for certain other function?
So sorry, Sneha, I heard you perfectly well up to the last sentence or so. Am I right in saying that you're asking, could one use this kind of method for, say, Dirichlet L functions or other L functions?
Right, to verify the Riemann hypothesis for those up to.
Yeah. So yeah, that's a very good question. The short answer is yes. So the reason I won't go back in the slide, but I gave 2 dates for Dave Platt's work on this. One was his thesis in 2011, one was his paper in 2017. So his thesis actually had 2 main components. The first one was doing this algorithm for the zeta function and then applying it to counting the number of primes up to like 10 to the 20 or something exactly. And the second one was doing this arrangement for Dirichlet L functions. So obviously things get more complicated with Dirichlet L functions because there's infinitely many of them. There's infinitely many q, and for each q there are 5 q characters to look at. So there's stuff to do, but what he did was to say, I think I'm getting this right, for all q prime, I mean, maybe it could be for all q, but let's just say for all q prime. For all q prime and less than 400,000, the Riemann hypothesis is true for Dirichlet L functions L, the character chi mod q, up to height like 100 over q or something. Or maybe it was like 10 to the 8 over q. So some height that decreased as q went up. So for L functions with a very high conductor, q like 400,000, the height to which he proved it was a bit lower than for Dirichlet L functions with conductor q, where q was say 7 or something. So you get this thing of as q gets bigger, he's using exactly this method to prove the generalized Riemann hypothesis in shorter and shorter heights as the q gets bigger and bigger. And that would have appeared as a paper in, I don't know, 2015 or 2016. That was the earlier paper that he had. So yes, absolutely, one could do that. Without talking about for too much more time, the often, this is my take on it, when one moves, in a sense, further away from the Riemann zeta function, or what does that mean? I guess q is bigger and bigger. You're more interested in what's happening lower down. You're more interested in what's happening near a possible Siegel zero, or what's happening near the real axis, or Charles conjecture, or all sorts of stuff. So it makes sense that in his computations, you're decreasing the height as you go further and further. You've got to do something, otherwise the computation is going to take forever. So decrease the height, because what you really care about is that there are no Siegel zeros, so no zeros on the real axis. So suppose I give you an L function, L character chi, and chi with conductor Q, and Q is like 10 to the 1,000, say. Yeah, I guess I could verify the generalized Riemann hypothesis for that character up to height 1,000. But I'm more interested, I suppose, at that level of verifying up to height, 0.0001, just to make sure there are no zeros lying on the real axis. And this doesn't vanish at the central point. I guess that's the other thing, that L of a half chi doesn't vanish. So yes, you can do this exactly for the Dirichlet L functions. Other people have done similar things for Dedekind zeta functions. Now then that's even more involved, because you've got, R1 real places and R2 complex places, or the other way around, I can't quite remember. So you've got even more things you have to keep a hold of. But yeah, so the pioneering paper in that area is done by Robert Rumley in the, I want to say, the 80s. So yeah, absolutely, you can do this kind of scheme for more generalized functions.
Okay, thank you.
Yeah, so Professor Sophie, you wanted to ask, or should I read out your question? I think you're not audible. First, please unmute yourself. Okay, yeah, so I'm going to read out since he's not audible. So his question is, any improvements on the percentage of zeros lying on the critical line in the spirit of Liouville's classical theorem to the effect that 50% of zeros lie in the critical line? So can you see the chart, or yeah?
Yeah. So yeah, in this paper, we didn't look at the question of the proportion of zeros that lie on the critical line. That's a very interesting question, and I think it's an area ripe for future research, but it's not amenable to the same analysis as what we're doing here. So here, we were just trying to verify the Riemann hypothesis up to a certain fixed height, and to make that height as high as we could go before we all just got sick of staring at computer screens. So your question about the percentage of zeros, yeah, this is an interesting question. I mean, in the 40s, Selberg proved there's a positive proportion of zeros on the critical line. Who knows what that proportion is? And one of Titchmarsh's students, Min, S.H. Min, wrote his thesis in Oxford, and I've seen it in the library there, and he actually goes through Selberg's argument and says something like, 1 over 14 million% of zeros lie on the critical line. I actually have some photocopied version somewhere where he doesn't say 1 over 14 million, he gives a number, 1 over 13,700,000 and whatever, so he figures out what the number is. So a small percentage. And then this number was boosted by Levinson in the 70s, I think, to a third. And then to Brian Conry in a huge paper in 1989, where he gets it to 2/5. So the paper, it might even say at least 2/5 or more than 2/5 of the zeros of a zeta function on the critical line. So 2/5 or 40% was done in 1989, and it's more or less stayed at that value. So again, we could talk about the reasons why, but everyone is more or less improving on what the previous people have done quite cleverly. They're not just mucking around, they're improving it cleverly, but the improvements are quite small. So the record now, look, it might be 42% or something. I mean, it's not, as far as I know, it's not, it's certainly less than 43. Maybe it's 42, maybe it's 41.5 or something. So as far as I know, that's as good as it's got. And it's not immediately clear to me how you would improve that further. You could try to do what other people were doing and run it on a very large computer, but some of these problems, well, some of these problems you have to choose a polynomial which makes a certain function large, say. Now, you could choose a polynomial of arbitrary degree. It could have degree 1000, say. So you could have a whole lot of computational fun with that. Now, it turns out that in practice, the polynomials that work exceptionally well are ones of low degree. And who knows why that happens. But what that means is that there's no real point in trying to find some exotic polynomial of degree 10,000 when all the polynomials that everyone's using have degree 2 or 3. Those, for whatever reason, seem to be the best ones to use. And so in that sense, it's harder to put that program of research into a computational structure and to say, now we're going to spend 4 hours and for 4 years and 850 core hours to improve. So yeah, I've not written a paper in that area. I'm not an expert in it, but from what I have read, it seems that those results are starting to flatten out in terms of the improvement.
Yeah. So Tim, yeah, one is this technical question: what software has been used which allows 100 bits of precision? That is one question.
Sorry. So just Shanta, so I can understand. You're saying where, as in
no.
what?
Which software has been used which allows 100 bits of precision? That's that's one of the questions. So what is the name of software, or which software?
Oh, I see. So it's ARB, I think. It's at the back of the paper. So sorry, I don't like saying everything's in the paper, but I think it's ARB. I as you can tell, I have no idea, but but I did proofread the paper. So yeah, ARB library or something. I think that's what Dave used for his interval arithmetic.
So I'll take one last question, then we'll finish. So this is question from Riddhi again. So question is it possible to check if there are rational zeros or not? Is it possible to check if there are rational zeros or not? That's the question.
Yes, sorry. Is it possible to see whether there are what zeros?
Rational zeros.
Zeros which are rational numbers.
Oh, yeah. That's an excellent question. Yeah. I mean, the cheeky answer is to say yes. The 0 at -2. That's rational. I mean, but so. Forget about those. Take a non-trivial 0. I don't think anyone has any idea of how to prove that any 0, just take the first one. I don't think anyone has an idea of how to prove that it's rational or irrational. And there's two kind of sort of comments I often make about this. One is, let's take a number that's much more well known, like Euler's constant gamma. Like 0.57. It's sum of the harmonic series 1 over n up to x minus log n. No one knows whether that's rational or irrational. I mean, there's these proofs like if it is rational in a over b, when a over b are in lowest terms, then b has to be bigger than 10 to the 10 to the 10 to the 10 or something. But I don't think anyone has any idea about how to prove that that's rational. I mean, everyone surely assumes it's irrational and transcendental and so on. So there are these kind of wacky numbers that probably we're just never going to know about. Now take a Riemann zeta function. I think we're going to know even less about the zeros because the location, the first 0 in my mind is not a number like square root 2. I mean, square root 2, okay, fine. We know it's algebraic, but square root 2 has some kind of algebraic significance. It appears in some sort of equation. In my mind, the first 0 appears in no equation. I don't know of anything that connects the first 0 with other stuff that we know about. I mean, I guess we could play games with pi and so on, but I think the analogy kind of breaks down with the zeta zeros in that the only way we know how to find them, in a loose sense, is to look at an interval and then make that interval smaller and smaller. Now you might say that's how we find square root 2 as well. Okay, fine, but square root 2 has some sort of extra significance. And I think until we have that extra significance mapped out, even if indeed there is any, I think it's an excellent question to ask. And there's all manner of questions about other zeros linearly independent over the rationals, say. So I gave a talk it was a month ago or 2 months ago. Sneha invited me, and I saw Kaushik there as well at IIT Delhi, talking about the supposed linear independence of the zeros. So suppose I say the first zero is at 14.1 or something, and the second one's at 21 point something. Can I find integers C1 and C2 such that C1 times the first one plus C2 times the second one equals 0? So like 10 times this minus 7 times that, say. Presumably not, as in everyone thinks the answer is no, you can't find any integers apart from the trivial one of 0 and 0. But good luck. I mean, that seems, the Riemann hypothesis seems hard, the simplicity of the zeros seems harder, and proving that the zeros are linear independent seems impossible. And so wrapped up with that kind of question is well, just say 1 0. I mean, could you just show me that 1 0 is rational or irrational? I mean, we can ask that question, we can frame the question. I just don't think there's any tools we have available at the moment to put that into practice. So yeah, it's an excellent question, and it's, I guess, a classic embarrassment in the field that my only answer is to say it's an excellent question. Not only do I not know, but I don't know anyone who has any idea about how one would go about answering that.
Okay, thanks, Tim. So yeah, thanks, Tim, for a nice lecture and for the interesting talk. So let's thank Tim once again.